Hello everyone, in this lecture we will be having a look into a problem which will require a simple application of Burnside Lemma. Here's a view of this problem. In how many different ways can the vertices of a regular hexagon be colored using C different colors? Now recall from our previous treatment that two colorings are essentially the same. They are same if one can be obtained by another coloring by a simple rotation or a reflection. So therefore this problem is asking for essentially different colorings up to rotations and reflections. Just to give you an idea, consider this hexagon here and another one, probably this one. Oops, so let's make it okay. And consider these following colorings. So this one, the first one, has all vertices yellow except this one red, whereas the second coloring is all vertices yellow as well, however another vertex is red. Now these two colorings are actually considered the same for the purposes of our problem. They are not different colorings because we know that we can obtain the coloring on the right side by simply rotating the coloring on the left side by a 60-degree rotation. So those two colorings are considered the same. We do not want to overcount. There are 6 of these and we will just consider these as 1. So what matters for us is the number of essentially different colorings that are different, that you cannot obtain that coloring by a rotation or reflection of another coloring. In fact, we learned by Burnside Lemma, so let me remind you of the Burnside Lemma. Burnside Lemma gives us exactly that. So the number of colorings, essential number of orbits, but orbits is simply essentially different coloring. So let me write that down. So this is simply essentially different colorings. Obviously when I say essential different, I mean up to rotation and reflection, but we can easily change the setup and we can say, hey, I'm only interested up to rotation. Reflection is not allowed because this shape is not transparent or things like that. But anyhow, so the formula would be 1 over g, the size g of the group of symmetries of the hexagon in this example, over the summation of g in g and each individual symmetries in that group, and the summands are the fix of g. So we will explain these, but first let's investigate this group g, our group of symmetries for this regular hexagon. As usual, the identity is one of the elements of this group of symmetries. Basically do nothing. Then we have a bunch of rotations. The 60-degree rotation, like the one in this example, would be one of them. So let me call it R1. So we have the 120-degree rotation, the 180, the 240, and the 300-degree rotations. These are all different symmetries of this regular hexagon. But then, beyond these symmetries, we have also symmetries of rotational symmetries. We have also reflectional symmetries, and we have actually 2 types of reflectional symmetries. When you think about it, let me draw a new picture here. So this is our hexagon. So in that hexagon, we have one type of rotation, reflectional symmetry is obtained by drawing the axis joining 2 opposite vertices. So we're trying to color the vertices, and we are creating this symmetry joining 2 opposite vertices, and let's call these as sub I. In that case, we have 3 of those. 1, 2, 3. Notice that these 3 lines will concur at the center of that hexagon, S2 and S3. Finally, we also have the reflection in an axis joining the midpoints of opposite edges. So that would be one of them. So let's call them T sub I. And again, we have 3 of those. So we are simply joining the midpoints of opposite vertices. So therefore I have T1, T2, T3. So therefore the size of G is simply 12. We have 12 symmetries of regular hexagon, hexagon. Now in the second step, so now we know exactly what this coefficient is. Now for each of these symmetries of the regular hexagon, what we will do is we will compute the fix of G. So what do we mean by that? So the simple explanation is that in order to work out how many different patterns, how many different essentially different colorings, or how many different patterns there are, we need to work out how many colorings are fixed by each of these symmetries. You can actually work this out by considering the permutations of vertices corresponding to each of these symmetries, and in fact you can represent each of these symmetries by a permutation. So for instance, if I numbered each of these vertices as 1, 2, 3, 4, 5, and 6, and consider for instance R2. R2 is simply the 120 degree rotation, say clockwise rotation. So the representation of this symmetry as a permutation will be that we have the permutation 1, 3, 5. We will have a cycle there, 1, 3, 5, 1, 3, 5, and then we will have 2, 4, 6 cycling around, 2, 4. And last time we discussed that this notation is awesome for us, so we really enjoy this notation because it helps us establish how many cycles there are. So the number of cycles will ultimately tell us the number of colorings that will be fixed. That will be fixed, and those colorings are important for us because they will tell us the essential different colorings. So in this case, because we have 2 cycles here, so therefore we will have C to the power, so C different ways we can color 1, 3, 5, and C different ways we can color 2, 4, 6, independent of each other. Therefore we can apply the multiplication rule, and we will get C squared different ways to color the contribution, the fix of G, the fix of, in that case, R2 will be C squared. So therefore the fix of R2 we will say is equal to C squared. So again, a coloring is fixed by a symmetry whenever all the vertices in each of the cycles of this permutation are assigned the same color, because you need to do that, because when you apply R2 to a coloring, let's say so this first vertex will be mapped onto this one, so therefore 1 and 3 must be the same color, but then the vertex 3 will be going on to vertex 5, so 5 will be the same, so those 3 would have to be the same color once you apply R2 and when you calculate the fix of R2. Now we can go ahead and actually calculate each of these on a new page, and then we will make use of this formula, and then that would reveal the answer. So let me open a new page here. So let's start with the fix of E. Well, the fix of E would be so how many colorings are fixed by applying the identity, all of them. So what is all of them? So we have each vertex can be colored in C different ways, and we have 6 vertices, so that's C to the power 6. So let's move on to the next one. So that one was pretty easy actually. What about R1? Remember, R1 is the 60 degree rotation. Now in the 60 degree rotation, when you think about it, this vertex, so we have our vertices 1, 2, 3, 4, 5, 6. So vertex 1 will be going to vertex 2 after you apply this symmetry. 2 will be going into 3, 3 will be 4, 4, 5. So therefore, in that sense, 1 and 2 must be colored the same way. 2 and 3 must have the same color, and so on. So there are only C different ways you can color, because each of these vertices have to be the same color, and we have only C different colors, so therefore this is C. Now fix of R2. Well, we already did it using the group notation, but we just realized it's C2 because 1, 3, 5 should be the same color. Similarly, 2, 4, 6 must be the same color, and there we go. How about fix of R3? So that would be a 180 degree rotation. So therefore, in this case, 1 and 4 will be the same color, and because 1 will be mapped onto 4, 4 will be mapped onto 1, so therefore that's one cycle here. And then 2 and 5 are mapped onto each other, that's another cycle, and 3 and 6 are mapped onto each other. In fact, if you want to use the cycle notation for using the cycle notation, R3 is simply 1, 4, 2, 5, and 3, 6. So as such, we can see there are 3 cycles, and as a result, this would be C cubed. Similarly, fix of R4, which is the 240 degree rotation. So this one will be mapped onto 5, 5 will be mapped onto 2, so 1 will be mapped onto 1, 2, 3, 4, 5. 5 will be mapped onto 1, 2, 3, 4, 3. 3 will be mapped onto 1. So let me write that down actually. R4 is simply 1 will be mapped onto 5. Oh, sorry. Yeah, that's closing it. My bad. So 1 will be mapped onto 5. 5 is mapped onto 3. And 3 is mapped back onto 1. And finally, 2 is mapped onto 6. 6 is mapped onto 4, and so on. So again, we have 2 cycles, so that's C squared as well. So fix of R5, that would simply be a 300 degree rotation. So 1 will be mapped onto 6, 6 will be mapped onto 5, and so on. So R5 is 1 is mapped onto 6, 6 is mapped onto 5, 5 into 4, 4 into 3, 3 into 2, and 2 back onto 1. So therefore there's only one single cycle, so that's again C. And just for completeness sake, let me remind you that R2 was simply 1, 3, 5 and 2, 4, 6, and finally R1, I should say. So it would be 1 to 2, 2 to 3, 4, 5, and 6. So just for the completeness sake, I showed you the permutation representation of each of these. So therefore, you can either create a graphical representation, a picture if you will, or you can actually use the cycle notation of permutations. Either way is good to establish the fix of each of these symmetries. Next, we need to look at so we are done with the rotations. We need to look at the reflection. So what is the fix of S sub 1? Recall that S sub 1, let me draw a new picture here. So S sub 1 will be the reflection joining 2 opposite vertices, let's say this one, and the others are symmetric, so we will just simply go ahead and multiply whatever we got by 3. So how many cycles are there? So we have 1, 2, 3, 4, 5, 6. So let's call this symmetry here, going through those opposite vertices 2 and 5. So how many cycles? Well, obviously 1 is after the reflection is taken, 2 is mapped back onto 2, so therefore there's a cycle here. 3 is mapped onto 1 is mapped onto 3, 3 is moved back onto 1, so therefore those two are a cycle. 4 and 6 are a cycle, and then 5 is a cycle by itself. So therefore, if you will, S1 will be simply equal to, well, depending on how, okay, so S1 will be 2 is a cycle by itself, 1 and 3 are a cycle, 4 and 6 are a cycle, and then 5 is a cycle by itself. But then we usually don't represent it like this. We simply omit the ones that the cycles with only one element in it, so that's a more traditional form of writing this. So in total we have 1, 2, 3, 4 cycles. For each cycle can be colored in C different ways, so therefore C to the power 4. But then fix of S2 and fix of S3 are no different. They are just the same, so they are also C to the 4. Now the remaining one is the fix of T sub 1 through T sub 3. Again, they are all the same, so I will just write it T sub I. So we have, let's think about it. So we have our hexagon. So here is a symmetry axis of the reflection and symmetry axis. So 1, 2, 3, 4, 5, and 6. So 1 will be mapped onto 2, 2 will be mapped back onto 1, 3 to 6, 6 to 3, 4 to 5, 5 to 4. So therefore T sub, let's call it T sub 1, I guess. So T sub 1 will be simply equal to, so 1 will be mapped onto 2, 2 back onto 1, 3 to 6, 6 to 3, and then finally 4 to 5, 5 to 4. And as a result, we have 1, 2, 3 cycles. Each cycle can be colored in C different ways, C cubed. And we have, this works for I equals 1, 2, 3. And as you can see, you can similarly write down C2, C3, and T2, T3 as well. Finally, we can find out what is the number of orbits in our, or number of different coloring patterns, or essential different colorings, whichever you want to call it. So 1 over 12, we have 12 symmetries, and then we have a summation sign. Remember the formula. So we have 1 C to the 6, right? So we have just 1 C to the 6, and then we don't have C to the 5, we have C to the 4, we have 1 here, 2 more here, so in total we have 3 C to the 4. Then we have C cubes, a bunch of C cubes. We have our 3 C cubed, and then we have 3 more here, so in total we have 4 C cubed, 4 C cubed. Let me erase this portion of my picture here. What else do we have? How many C squares do we have? We have R2 is a C squared, R4 is a square, so we have 2 of them. We have 2 C squared. And how many C's? We have 1, 2 C's, so plus 2C, and that would actually solve the problem. So we were able to find that this is the number of patterns, coloring patterns, for the regular hexagon up to rotation and reflections. Let me actually move a little bit beyond this. Suppose that we have C is equal to 2. We have 2 colors only, black and white. How many different ways can you color? Suppose that this is a necklace, and in that necklace we have beads, and the beads are, so this is no different than that problem. So we have the beads, we can color the beads. In how many different ways can we color it? Obviously, the necklace can be rotated, and you can also flip it to reflect it as well. So that's a good example. So the essential different colorings would be 1 over 12 times 2 to the 6 plus 3 times 2 to the 4 plus 4 times 2 cubed plus 2 times 2 squared plus 2 times 2. That would be equal to 1 over 12. 2 to the 6 is 64, plus 2 to the 4, 16 times 3 is 48, 8 times 4, what's that? 4 times 2, 8, and then we have a 4 here. So in total we have 12 plus 80 is 92, plus 64 would be 156, so therefore the answer would be 156 over 12. I know 144 is 12, so this one is 13. There are 13 essentially different coloring. Can you go ahead and draw these 13 different colorings? That would be a very, very nice exercise. So that ends our problem. So hope to see you in our next video.